Hello linear algebra students. This video lesson is on orthogonality. Recall that two vectors in Rn are said to be orthogonal if and only if their dot product is 0. Now in 2 and 3D, that means that the vectors are perpendicular. Suppose we have a vector b in Rn, but v is not in some vector space V that's a subset of Rn. The vector b can be projected to the vector space V, meaning that b can be decomposed into orthogonal vectors a and a perpendicular, such that a is in the vector space. This vector a is called the projection of b onto v. Note that if v is the span of just one vector, then a and a perpendicular can be found as follows. This is something that we did in an earlier unit. So let's take a look at this image that we have here. Now these are three-dimensional vectors, but we are looking at them in a two-dimensional context. We are going to project vector b onto vector v, or we can also say onto the space spanned by vector v. If we span vector v, we'll get all linear combinations of it, and that'll produce this line that passes through 3 space and contains the origin. Keep in mind that the origin would be right here. So we're going to decompose vector b into two vectors a and a perpendicular, where a is in this vector space. So imagine drawing a right triangle, where a is this green vector, and a perpendicular is this red vector. And we have that they are perpendicular, or we can just say orthogonal. Now the formulas that we used are right here. The projection of b onto the vector space V is equal to, we do the dot product of b and v in the numerator, which will give us a scalar, and divide that by the scalar, that's a dot product of v with itself. Ultimately, what we have in these parentheses is a scalar, and then we scale a vector v by that scalar, and that will give me the vector a that I'm after. And then we know that vector a plus vector a orthogonal should equal vector b. Therefore, vector a orthogonal can be computed by simply doing vector b minus vector a. Okay, let's go ahead and find what these vectors are. Vector a, which is the projection onto vector space V of vector b. We're going to do a dot product of b and this vector here. So we just multiply corresponding entries and then add the results. So we get 2 times 3, which is 6. 2 times 2 is 4. And then 1 times negative 2 is negative 2. And then divide that by v dot itself. So dot this vector with itself, we would have 2 times 2, which is 4, plus 2 times 2, which is another 4, plus negative 2 times negative 2, which is yet another 4. And this ultimately will be a scalar that will multiply to vector v. Now simplifying these numbers, we wind up getting 8/12, which is the same thing as 2/3. So we just have to do 2/3 of vector v, and then multiply vector v by 2/3. You can distribute the 2/3 through each component, and we're going to get the result 4/3, 4/3, negative 4/3. And this is our green vector in the image. Now to find the red vector, a orthogonal, we simply do vector b minus the vector a that we just found. Vector b being 3, 2, 1. We're going to remove from this vector a that we just found. 3 minus 4/3 is 5/3. 2 minus 4/3 is 2/3. And 1 minus negative 4/3 will be 1 plus 4/3, which is 7/3. And this is the red vector in our image. So notice that the green vector is in fact in our vector space V. It's a scalar multiple of v, so it's in the span of vector v. It's on that orange line. And further notice that these two vectors are orthogonal. If you do the dot product of these two vectors, you get 20/9 plus 8/9, that's 28/9, and then minus 28/9, and you do get 0. And furthermore, verify that b in fact can be decomposed into these two vectors. Adding these two vectors together, we get 9/3 is the first component, which is 3. Second component is 6/3, which is 2. And the final component is 3/3, which is 1, confirming that we get the vector b back. Okay, looking at Desmos 3D, we have our two vectors. This first vector here is 2, 2, negative 2, and then we have the vector b, 3, 2, 1. I'm going to go ahead and get rid of all of the axes to declutter this. Now the span of vector v is this orange line, and we're going to project vector b, which is right here, down to this orange line. And we determined that we needed to do 2/3 of the basis vector for the vector space, which is this vector here. And then we found our orthogonal complement. And this creates a right angle right here, and we've deconstructed vector B into a vector A, which is in this vector space, plus some orthogonal vector A orthogonal. And this red vector is currently being drawn as if it's originating from the tip of our projection vector, but normally if we position all vectors that are relevant at the origin, we would simply move that vector to here, and then we can still see that the green vector plus the red vector ultimately will yield this vector B. Okay, let's go to the next page. Now, an orthogonal basis of a subspace is a basis where all vectors in the basis are orthogonal to each other. That means if you were to do the dot product of any pairing of vectors in the basis, you would get 0. Show that the basis below, which spans a plane in R3, is an orthogonal basis. So we have two three-dimensional vectors, and they are not multiples of each other, so they are linearly independent. So when you span them, you will get a plane in 3 space. But now we want to show that the two vectors are not only linearly independent, but that they are orthogonal. So we will do their dot product. Let's go ahead and name the two vectors in this span, v1 and v2. And if we do their dot product, multiplying corresponding entries and adding the results, we get 2 plus 0 minus 2, and sure enough, we do get 0. This suggests that the two vectors are already orthogonal to each other. So we call this an orthogonal basis of this plane. Now, if you have an orthogonal basis that has some required number of vectors in it, like m vectors, and it's a basis for some vector space V, which is a subspace of Rn, then the vector A, which is the projection of the vector B onto this vector space V, and its orthogonal complement, A orthogonal, can be computed as follows. So the formula that we're already familiar with generalizes, and we basically do the exact same calculation, but we do it for every vector that's in this orthogonal basis up until we get through all of them. And we add all those results together, and that's how we can construct this projection vector that we're calling A, or in more formal notation, the projection of vector B onto vector space V. And then we'll find the orthogonal vector by just simply doing vector B minus vector A once vector A is calculated. Okay, project the vector B shown below. So it's the same vector B as from before, 3, 2, 1. To vector space V, capital V, mentioned above, right here. And then decompose vector B as described above. All right, so this time our space is a plane, not just a line. The two vectors in our basis are orthogonal to each other. I know this image here that does not appear to be the case, but you do want to imagine this being a right angle. We're just looking at it from a skewed angle. But we do have orthogonal vectors v1, v2, but they will span some sort of plane, of which I've just drawn a portion. And then we are going to project this vector b, which is not on this plane, to that plane. So there will be some vector that we're going to call the projection. It'll end right around here, and I'm imagining a right triangle as I draw these, and then some orthogonal component, and these will make a right angle. And in this image, the green vector that we're after is the projection vector. We're calling it A for short, but it's the projection of B onto this vector space V, and this plane here is our vector space, and we calculate it as follows. Vector A, which is the projection onto vector space capital V of vector B, is equal to, and I'll do this part of our calculation and then a second part of our calculation, and then we'll stop because this vector space V only has two orthogonal basis vectors in it. So we'll do vector B and dot that with vector 1, divide by the dot product of vector 1 with itself, and then multiply this scalar by vector 1. And then we're going to repeat this, but using vector 2. Okay, now let's calculate all these dot products. We're going to dot product vector B with vector v1. That will give us 6 plus 4 minus 2, or 8, divided by, and the dot vector v1 with itself will be 4 plus 4 plus 4, which is 12. And then we'll multiply this by vector 1, plus, now let's do the other dot products, dot B with vector 2. That'll give us 3 plus 0 plus 1, so it'll give us 4 in the numerator. And then v2 dot with itself will be 1 plus 1, or just 2. And we'll multiply that by vector 2. So 8/12 is the same thing as 2/3. We're going to do 2/3 of vector 1 again. That gives me 4/3, 4/3, negative 4/3. and then plus 2 of vector 2, which will give me 2, 0, 2. And then I add these together, and I get the following result. 4/3 plus 6/3 is 10/3. 4/3 plus 0 is 4/3, and negative 4/3 plus 6/3 is 2/3. And this is the green vector in our image. Now we'll find the orthogonal complement. A orthogonal is equal to vector B minus the vector A that we just found, giving us 9/3 minus 10/3, so negative 1/3. 6/3 minus 4/3 is 2/3, and 1 minus 2/3 is 1/3. And this vector we just arrived at is the red vector in our image. Well, the green vector should be in our vector space because it was an obvious linear combination of the two basis vectors, so it'll be on the plane, and then the red vector is orthogonal to it. If we do the dot product of these two vectors, we get negative 10/9 plus 8/9 plus 2/9, and that does zero out. So these two vectors are orthogonal. Furthermore, they do add to the vector B. 10/3 minus 1/3 is 9/3, which is 3. 4/3 plus 2/3 is 6/3, which is 2. And 2/3 plus 1/3 is 3/3, which is 1. So their sum is in fact vector B, and they are orthogonal, and the green vector is in the vector space. Let's look at this one with technology. So the two basis vectors I have graphed here in orange, and then the vector B is this gray vector that you're seeing here. Let's go ahead and reveal the plane. That is the span of those two basis vectors. So this is our vector space, and we want to project this vector here that's not terminating on that plane. We want to project it to that plane. I'm going to hide all the clutter and just focus on the fact that we have a vector that we want to project to a plane. And we just discovered that that vector is the vector 10/3, 4/3, 2/3, which is plotted here. You can see it's in the plane. And then we found the orthogonal component. This makes a right triangle right here. The green and the red are orthogonal to each other, and they add together to make the vector B. Let me put the axes back in here. And ordinarily, we do have the red vector currently positioned so that it begins at the head of the green vector. But if you originate this at the origin, that would make our vectors look like this. And it's still the case that the green vector plus the red vector will equal our vector B. And one more thing to realize is that this green vector terminates at a location on the plane that is considered to be the closest location to the head of the vector B that we're projecting to that plane. If you pick any other location on this plane and calculate its distance from that point to the head of the vector B, you will get a longer distance than this red distance. So you can think of a projection vector, which is the green vector, as being the closest vector in a space to a vector that's not in the space. Okay, let's go to the next page. Now this page is dedicated to finding an orthogonal basis if we don't have one to begin with. On the last page, we saw a formula that we can use to find a projection vector, but it required that the basis you're working with be an orthogonal basis. And if that's the case, then you can use this formula right here to find a projection vector rather easily. And so we're going to learn something called the Gram-Schmidt process for taking any basis of a vector space and converting it into an orthogonal basis. And if we scan back to our first page, we found this red vector, which is orthogonal to the green vector, by doing a vector B minus its projection vector. And that led to an orthogonal vector. You see that happening in this situation as well. In order to find this red vector, we had to first find the projection vector of B onto this space, which was vector A, and then we simply did B minus that projection vector, and that's how we found this orthogonal vector. So using these ideas, we can follow the process you see here to find orthogonal vectors out of vectors that are non-orthogonal. So before we demonstrate the process, I want to explore these three vectors you see right here. If you do the dot product of any pairing of them, you will not get 0. There are no two vectors in here that are orthogonal to each other. But we want to construct an orthogonal basis that spans the same space. We will use u's to represent the original vectors, which may not be orthogonal to each other, and we use v's to represent the results of this process, which will represent an orthogonal basis. So the v's will all be orthogonal to each other, even if the u's are not. I'm going to demonstrate visually what we're going to do here with these three vectors. Using our Desmos 3D, I have the three vectors plotted here. You can see that none of them are coplanar, so they are all linearly independent. Therefore, they will span all of our three, but also that they are not perpendicular to each other. All right, the process we're going to follow, we're going to ignore the third vector in the list. Just focus on the first two vectors in the list. They are not orthogonal to each other. Now consider the space that they span. They span this plane right here, the plane that they are both in. They form a basis for this plane, but we want to form an orthogonal basis. So what we're going to do is we're going to leave the first vector in our list untouched, but we're going to project this vector to this vector here, and then figure out its orthogonal complement, and then keep that red orthogonal vector, basically replace this vector here with the red orthogonal vector that we find following this process. So I'm going to project this second vector to this first vector, and we get this vector here. Then I'll find the orthogonal complement, which will be that red vector. And then, of course, we'll shift that so that it originates at the origin. And then I'm going to get rid of the projection vector, get rid of the second vector, and keep the first vector, and use this now as my basis for this space. And notice that the result is guaranteed to be two orthogonal vectors that are still in the space, so they still span the same space. Now we're going to take into account the third vector from our list. This is u3. You'll see u3 is not on the plane. So then we're going to project this vector here, u3, to this plane. And we can do that using this as my v1, v2 because they're orthogonal. So we can use the formulas we talked about and project this u3 to this vector space v spanned by these two red vectors. That gives me this vector here. Then we will find its orthogonal complement, and then we'll reposition this red vector so that it originates also from the origin. And then I can get rid of the projection vector and get rid of u3. And like that, I have found three vectors that are all orthogonal to each other. Okay, back to our notes. Let's actually do this process now. These formulas that you see here do exactly what we just demonstrated with the visual. So our first vector that we're going to use for our orthogonal basis will simply be the first vector in our non-orthogonal basis. So just let v1 be the same thing as u1. Now we'll construct v2 following this formula here. So that'll be vector u2 minus, and then I'll dot u2 with v1, divide that by v1 dot with itself, and then multiply that by vector v1. So u2 is the second vector in our non-orthogonal list, so negative 1, 1, 2. Dot this vector with v1, and v1 we're saying is the first vector, so we're just dotting these two vectors, and we get negative 1 plus 0 plus 4. That gives us 3. And then we're going to dot v1 with itself, and we're saying that this vector here is v1. So dot that vector with itself. We get 1 plus 4, which is 5. And we do 3/5 of vector 1, which is 1, 0, 2. And then combining these together, we get the following result. Negative 8/5, 1, 4/5. And now we just need to construct v3. So we're going to stop with this formula here and then be done. Let's do v3. Vector v3 is equal to vector u3 minus u3 dot v1 over v1 dot itself times vector v1, and then minus u3 dot vector 2 divided by vector 2 dot with itself, and then all times vector 2. So u3 is the vector 0, 2, 1. Now I'm doing u3 dot v1. So I'm dotting these two vectors here, and that gives me 0 plus 0 plus 2. And then v1 dot with itself is 1 plus 4, or 5. And then multiply that by vector v1, and v1 is just the first, it's the same thing as u1. And then minus, and now we're going to notice that some of our dot products start to get a little bit more complicated, more fractions involved, because I need to do u3 dot v2. Well, u3 is here, and v2 is over here. We need to dot these two vectors together. That gives me 0 plus 2 plus 4/5. That's going to give me 14/5. And then we need to do vector v2 dot with itself. So focusing on that highlighted vector, dot that with itself, we will have 64/25 plus 1 plus 16/25. And when you add all those together, you get 105/25. And then we'll multiply this scalar by vector v2, which is negative 8/5, 1, 4/5. So the calculations can become quite tedious. Feel free to use technology to make sure you're doing your fractions correctly. This coefficient will just become 2/3, making things a little bit easier to work with. And in the end, when I combine all of these vectors, I get the following result. 2/3, 4/3, -1/3. And this is my vector v3. Thus we construct an orthogonal basis that has the vectors v1 through v3. And we have our orthogonal basis comprised of these three vectors v1, v2, and v3 that we just calculated. And I want you to observe and verify that if you do the dot product of any pairing of vectors in this orthogonal basis, that you will get 0. Verify that claim, and that will confirm that we do have, in fact, an orthogonal basis. These three vectors, v1 through v3, are exactly these three red vectors that we showed over here in our visual. Okay, let's go to our next page. Recall that a unit vector is a vector whose magnitude is 1. Any non-zero vector v can be scaled to be a unit vector with the same direction by computing 1 over the magnitude, which will be a scalar, times the vector v, which action is called normalizing the vector v. An orthonormal basis of a subspace is an orthogonal basis where all vectors in the basis have a magnitude of 1. So we have a new term here, orthonormal basis. It's a special kind of orthogonal basis. If you take an orthogonal basis and scale all the vectors in that basis to have a length of 1, then you will have created an orthonormal basis. So let's convert the basis u1, u2, u3 equals these three vectors to an orthonormal basis. And we'll use w's to represent that the vectors in the orthogonal basis have been normalized. Now we've already done most of the work for this problem, and that is converting this non-orthogonal basis to an orthogonal basis. We're using v's to represent the fact that we have found an orthogonal basis. And bringing our work from above, we have these three vectors. So this was an orthogonal basis. Now we want to scale or each of these vectors so that we don't change its direction, but we change its magnitude to 1. In other words, we want to normalize each of these vectors. So we have to find the magnitudes of each one. So the magnitude of our first vector in our orthogonal basis, you dot the vector with itself and then take the square root. So we'll get 1 squared plus 0 squared plus 2 squared. So 1 plus 4 is 5, and take the square root. So vector v1 has a length or magnitude of radical 5. These next ones will be a little bit more complicated. The magnitude of v2 will be square all the components of v2, add them together, and then take the square root. So squaring the first component is 64/25. Squaring the middle component is 1. I'll write that as 25/25. And squaring the 4/5 is 16/25. And then take the square root of all this. And in the end, we are going to get the square root of 105 over the square root of 25, which is just 5. And then finally, the magnitude of that third vector in our orthogonal basis. Square the 2/3 is 4/9. Square the 4/3 is 16/9. And square the -1/3 is 1/9. Take the square root of all that, and we wind up getting the square root of 21 over the square root of 9, which is just 3. So these are the magnitudes, the current magnitudes of the vectors in my orthogonal basis. So if I now want to convert this all the way to an orthonormal basis, and we'll use w's to represent we've gone that far, then we just need to normalize the vectors v by dividing each one by its respective magnitude. So this will form the following basis. Divide v1, each component of v1, by its magnitude, and we get the first vector in our orthonormal basis is 1 over rad 5, 0 still, and 2 over rad 5. Continuing with this, vector v2, divide every component of vector v2 by the magnitude of v2. So to divide by the fractions, you're going to invert and multiply and then simplify, and we should get the following: -8 over radical 105, 5 over radical 105, and 4 over radical 105. And then doing the similar for w3, we're going to take v3, all of its components, and divide by the magnitude of v3. And this gives us, the first component will be 2 over radical 21, and then 4 over radical 21, and then finally -1 over radical 21. And here we have an orthonormal basis. These vectors are not only all perpendicular to each other, but they also all have magnitude 1. Now some interesting side notes. Let capital U be a square matrix whose columns form an orthonormal set. Then the following statements are true. The rows of U will also form an orthonormal set. Furthermore, the determinant of that matrix will either be 1 or -1. And then if you do the transpose of that matrix times itself in either order, you will always get the identity matrix. So if we take these three vectors that we just found that form an orthonormal set and convert that into a matrix, we get this 3 by 3 matrix, so it's a square matrix. The columns form an orthonormal set. Well, these theories say that the rows will also form an orthonormal set. So if you were to do the magnitude of any row vector, you would also get 1, and all the row vectors would be orthogonal to each other. If you calculate the determinant of this matrix, you will either get 1 or -1. And if you do the transpose of this matrix times itself in either order, you should get the identity matrix. I'm going to leave it to you to verify all of these claims on your own time. These are all curiosities and interesting tidbits regarding matrices whose columns form orthonormal sets. But let's go to the next page. Below is a summary of finding projections onto vector spaces. So we have 3 cases. We could have a basis that's presented just in general fashion. We'll use U's for those vectors. Let's call this a general basis. The vectors in this basis don't have to have any conditions. They just need to be linearly independent in order to form a basis. We'll use the V's to represent the conversion to an orthogonal basis, and then the W's to represent the conversion to an orthonormal basis. So if you're trying to take a vector B that's not in this vector space, but then project it to that vector space, basically trying to find the vector that's in the vector spaces that's quote-unquote closest to vector B, then we follow the following. Well, if you just have a general basis and the vectors aren't necessarily orthogonal, then we want to first convert the basis to an orthogonal basis before we can use a formula. If we do that, then we can use this formula that we introduced earlier to project vector B to the vector space. And then if we're doing an orthonormal basis, orthonormal is still orthogonal, so we could still use this formula but with W's instead of V's. But because we have orthonormal basis, all the magnitudes are 1, when you dot product a vector with itself, you get the square of its magnitude. So if you take a unit vector and dot it with itself, you will get 1. So all these denominators will become 1 if the vectors are also orthonormal. So your formula just boils down to this without any denominators at all needed. These just present 2 different options for finding a projection of a vector B onto a vector space. You have option 1 and option 2. You don't need to do both. You could do one or the other. Let's consider a fresh scenario. Let V equal the span of 2 vectors, u1 and u2, and those 2 vectors are 1, 0, 1 and 0, 1, 2. And we're going to project the vector B, which is 1, 1, 2. It's not in the span. We'll see this visually here in a moment. And we're going to project the vector B onto this vector space, capital V. Capital V, of course, will be a plane in 3 space because it's the span of 2 3-dimensional vectors that are independent of each other. And notice that these are, in fact, independent. They are not multiples of each other. Okay, let's go with this route here. We're going to first convert the non-orthogonal basis to an orthogonal basis and then use the given formula to find the projection vector. So the first vector in our orthogonal basis will be equal to the first vector in our general basis, that vector being 1, 0, 1. And then our second vector will be equal to u2 minus u2 dot v1 over v1 dot itself, and then times vector v1. So in this case, u2 is the vector 0, 1, 2. Remove. Let's dot u2 and v1. Well, u2 is here, and v1 is the same as u1, so we can just dot these 2 vectors. We get 0, 0, 2 added together, gives me a 2. And then dot v1 with itself, which is this vector here. We get 1 plus 1. We also get 2. And then multiply that by vector v1, which is 1, 0, 1. So in this case, we don't get any fractions, which is convenient. We get the vector -1, 1, 1. And then I stop here because our basis only had 2 vectors, u1, u2. So our orthogonal basis should also only have 2 vectors, v1, v2. Now we can do the projection formula. So we'll project vector B onto the space, and we just need to do the first 2 components of this general formula up here. And let's go ahead and calculate these dot products. So we'll take vector B, and dot it with vector v1. We get 1 plus 0 plus 2, so we get 3. And then dot v1 with itself. v1 is that highlighted vector. Dot that with itself. We get 1 plus 0 plus 1, so we get 2. And we'll multiply that by vector v1, which is currently highlighted, 1, 0, 1. Plus, now we're going to dot vector B with vector v2. v2 is this vector here. So dot the 2 current highlighted vectors. We're going to get -1 plus 2, which will give me 2. And then we're going to dot v2 with itself, and v2 is currently highlighted. Dotting that vector with itself, we have 1 plus 1 plus 1. We get 3. And then we'll multiply by v2, which is currently highlighted. And then calculating the result of this linear combination of vectors, we get the final vector of 5 6, 2/3, 13 6. And this is our projection vector. Let's see this with technology. So the two orange vectors are the two basis vectors for our vector space. And then this gray vector here is the vector b that we're going to project to that vector space. This plane here is the span of the two orange vectors. To find the projection of the gray vector onto the plane, we need to first find an orthogonal basis. And currently the two orange vectors are not orthogonal to each other. So we go through the process. So the first v1 we're going to keep is going to be the same thing as u1. So I'll just make it a red vector. Then we're going to project this orange vector to this red vector and then figure out the orthogonal complement and then keep that as my new vector, which will be this vector here, and then we don't need to focus on that one any longer. These two vectors are still a basis for our space, which I'll reveal again, but they're also orthogonal to each other. And these are the two vectors I'm going to use, therefore, in my formula to project this gray vector to this plane. The projection vector is this green vector. This is the vector that we just calculated as 5 6, 2/3, 13 6. And it's a linear combination of these two red basis vectors. In fact, looking at our notes, we see that if I do 3/2 of v1, which is this blue vector, and 2/3 of v2, which is that blue vector, and sure enough, when you add these together, they combine to be our projection vector. Okay, so this was using method 1 to find the projection vector. Method 2 is similar, except we go all the way to finding an orthonormal basis. So I need to calculate the magnitudes of my two vectors in my orthogonal basis. So the magnitude of vector 1 will be the square root of, and then square the components and add. So it's going to be the square root of 2. And the magnitude of vector 2, square the components and add, and take the square root, will be radical 3. So I'm going to normalize vector v1 to make it vector w1 by dividing every entry by radical 2. Or you can also leave that scale factor in front. So we do 1 over radical 2 times the vector 1 0 1. This is one way to leave it, or if you'd like, you can distribute the 1 over radical 2. The second unit vector in our orthonormal basis, do 1 over the magnitude of vector v2 and multiply that by vector v2. And you can distribute the 1 over radical 3 if you'd like, or leave it factored out in front. So now that I have my orthonormal basis, I can use this formula instead. Here's the formula we're going to use. So we're going to do vector b dot with vector w1. Vector b is here, and vector w1 is here. You may recall that if you do a vector dot a scalar times another vector, that scalar can just be brought to the front and just dot the two vectors. So the scalar 1 over radical 2, we can just leave it in the front. That makes calculating our dot products a little bit easier. So just dot the two orange highlighted vectors, and we get 1 plus 0 plus 2, which is 3. And then, of course, we have the 1 over radical 2. So we have 3 over radical 2 will be that result. And we're going to multiply that by vector w1. Well, w1 is 1 over radical 2 times the vector 1 0 1 plus. Now we're going to dot b with vector w2. And again, we can leave the scalar in the front, so just dot the orange highlighted vectors. We get negative 1 plus 1 plus 2, which is 2. And of course, that is divided by that scalar. And here's the dot product. And then multiply this by vector w2, which is 1 over that radical times the vector negative 1, 1, 1. So in the end, this will just wind up being 3/2 times the vector 1, 0, 1 plus 2/3 times the vector negative 1, 1. And so you see that this construction right here is the exact same construction that we saw up here, so naturally we get the same result. And this was using method 2. So in summary, method 2 basically requires you to go through partway through method 1 first. You have to do all these steps right here to use method 2 through its completion, or you could just use method 1 and just do these steps here. We leave it to you to decide which one you'd like to do better. You'll notice that method 2 does require a lot of radicals entering the equations, and that could complicate things, so perhaps you might settle on just doing method 1. Okay, let's go to the next page. Suppose a vector b is not in the range v of an injective linear transformation t from Rn to Rm. This would mean that the vector b cannot be an output vector of this particular transformation. But if we project vector b to the range, which means find the vector in the range that's closest to vector b, then the projection vector can be obtained by the transformation because it would be in the range. Thus reading here, then the projection of vector b onto the range, which we're using capital V to stand for the range, is in the range, and its unique preimage, and we say it's a unique preimage because we're assuming this is an injective linear transformation, so every vector in the output has a unique preimage, and its unique preimage is the closest approximate solution to t of x is equal to b. For the transformation below, find the closest solution to t of x is equal to 1, 1, 2. Right, we need to first verify that b is not in the range of this transformation and that this is in fact an injective transformation. Let's take a close look at the standard matrix for this transformation. If we put this in reduced row echelon form, we will get the following. This has pivots in the first and second columns, so the two columns are in fact linearly independent. So if we were solving a consistent system, there would be no free variables. No free variables meaning that the solution would be unique. So this is injective. There's no free columns, meaning each column has a pivot. That means that the columns are linearly independent, which means that this transformation is injective. Furthermore, we could say that the rank of this standard matrix is 2, which equals the number of columns. All of these communicate the same thing. So the range is the column space. It's the span of the two columns in our standard matrix. Graphically, those two columns are graphed as vectors. They're the two orange vectors. These are the same vectors we worked with on the previous slide. And the vector b on this previous slide is the vector that we're after in our range here. So this is vector b, and the columns of this matrix are vectors u1 and u2, all from the previous slide. So I'm using the same imagery that we have here before. Once again, we span the two basis vectors. So this is the range of this particular transformation. You see that it's not possible to therefore get this vector here by doing a linear combination of the two vectors in the standard matrix of this transformation. So we're going to project this vector to the range, and this green vector, which is in the range, is considered the closest vector that's in the range to the vector b. And now we want to solve this system instead. What linear combination of these two vectors, which are the columns of the standard matrix, will produce this projection vector? So if you were solving this from scratch, you would have to take these two non-orthogonal basis vectors and first convert them to an orthogonal basis, which we've already done on the previous page. Then we would have to use v1 and v2 to find the projection of this vector b onto this range. We're calling the range capital V, just to keep it short there, and we'll project our output vector b onto the range, and the work we did before gave us the projection vector 5, 6, 2/3, 13, 6. And this work was done on the previous page. But now we're going to go back to our transformation, back to u1, u2, and figure out what linear combination of these original vectors, u1, u2, will lead to this projection vector. So we can construct an augmented matrix using u1, u2 as the first two columns. This is simply our standard matrix of the transformation, and we want the output to be this vector here, which we know is in the range. So this should produce a consistent system. If you put this in reduced row echelon form, we can use technology to do that. We get the following. This vector x right here, this is in R2. So we could say vector x is equal to its components are x and y. So the first column here would be an x component and a y component. And so this tells us that x has to be 5, 6 and y has to be 2/3. And we're getting a unique result here because we have an injective linear transformation. But the vector x that we were after is equal to 5, 6, 2/3. Another way to present these findings is that if we do this vector, 5, 6, 2/3, multiply it by this standard matrix, and do matrix vector multiplication, we're essentially saying that 5/6 of the first column plus 2/3 of the second column should equal this output vector, which is the projection of vector b onto our range. Our answer was this vector here, which is the pre-image of the projection of b onto the range. Let's look at our image here, and we concluded that 5/6 of the first column, which is that vector, and 2/3 of the second column, which is that blue vector, when added together, so put them end to end, will produce the projection vector. So reframing our findings here, the vector x that I have highlighted here, 5, 6, 2/3, is the input vector whose output will be as close to the vector b as possible. So this process was really 2 pages of work because these 2 steps right here we did on the previous page. Also know that the process of finding this vector x, reading down here, this method of finding an input vector that maps as close as possible to vector b is called least squares approximation. Now it turns out that there's an alternate way to arrive at this same answer. This will be our last slide. Let A be m by n with rank n and where m is more than n. Then the least squares approximation to ax equals b is the unique solution to the system below. A transpose A times the vector x, which is what we're looking for, is equal to A transpose times b. We basically take ax equals b and multiply both sides on the left by A transpose. Now we're not going to go through the details of why this works. We'll just demonstrate how to use it. For the transformation below, find the closest solution to t of x equals 1, 1, 2. This is a repeat of the problem from the last page, but we're just using a new method to arrive at the conclusion. With this standard matrix of the transformation, we'll just call that A. And let's look at the conditions here of what has to be true about A. M has to be more than n, so it has to have more rows than columns, which is the case. M is 3 here and n is 2. And the rank has to be 2. So if we were to take A and put it in reduced row echelon form, we would once again get the same thing we had before. There'd be pivots in both columns. So all the conclusions we said before apply again. There's going to be no free columns when you're solving systems, so there's going to be no free variables. Each column has a pivot. The columns, therefore, are linearly independent, this meaning this transformation is injective. And furthermore, it means that the rank of this matrix A, which is the standard matrix of the transformation, is 2. And that matches the number of columns. So these conditions are satisfied. We have m is more than n, and we have the rank is equal to n, which is the number of columns of this matrix. Now we had to have more rows and columns because if we had the same number of rows and columns, and they were independent, and the rank was 3, the number of columns, then the range would be all of our 3. So there would be no vector not in the range. And if we had more columns than rows, then such a transformation cannot be injective because there will be guaranteed to be at least one free variable. Okay, so once we are convinced that the conditions are met, then we can use this formula with the transposes. So I'm going to write A transpose. A transpose is the transpose of this matrix here. Don't be working with the reduced row echelon form, but the transpose of the original matrix is 1, 0, 1, 0, 1, 2. We're going to multiply that by the matrix A, which is 1, 0, 1 as a column, 0, 1, 2 is the second column, times some vector x that we're after, is equal to A transpose times the vector b, which is not in our range. The transpose is a 2 by 3, and the original is a 3 by 2. So when you multiply these two matrices, you do get a 2 by 2. I'll leave it to you to confirm that you get the matrix 2, 2, 2, 5 times some vector x is equal to, and over here we have a 2 by 3 multiplied by a 3 by 1. So this will produce a 2 by 1, and I'll leave it to you to verify that that 2 by 1 will be the vector 3, 5. So we just solved this system, and I'll use an augmented matrix that I convert to reduced row echelon form, which tells me that the solution x has to be this vector 5, 6, 2/3. This is the same vector we got on the previous slide. Okay, this wraps up our discussion on orthogonality.